Hello everyone. I hope everybody is taking care of themselves, safe and sound at their places. So before we begin the lesson, I just wanted to let you know that if you have any questions, not just the subject, any crisis that you are going through, because there are so many things happening around, so many new things that you have to adjust yourself into, and so many unpredictable things. So if you feel overwhelmed and you need support, reach out to me or any other instructor. We are always here to help you guys out with the things that you're going through. So keep the connection, don't disconnect, because now that we are not going to be meeting regularly, this could create some disconnection between you guys and us. But try your best to give us an update, keep up with the work that we post, and like I said, don't be disconnected. Try your best to be engaged, and then whenever we are posting a lesson, try to go through it in a schedule. So if I post a video on Monday, don't wait until the next Monday to watch that. When I post a video on Monday, you have a plan. Okay, she's going to post videos in the morning, so I'm going to allocate this time slot to watch that video on that same day and make my notes. And then I'm going to list all the questions that I have, and then next day during the office hours, I'm planning to resolve those questions by talking to my instructor. So have a regular plan as you had when we were doing the face-to-face classes. When we were doing the face-to-face classes, you were required to come to class, you take notes, and you go through the stuff there with me. So try to stick to that similar plan rather than just skipping things, because at the end of the semester, otherwise you will get so overwhelmed if you don't plan ahead. Okay, right. So going back to the lesson, we were on chapter 7. Actually, I never got a chance to start chapter 7 with you guys. In fact, what I did is I gave you guys a chance to go through one part of chapter 7 on your own, which was sampling techniques. So I'm not going into that again, but we are going to start from here and then we will move to the next part. So sampling techniques is going to discuss about what are the different methods that you can select a sample, because the population oftentimes is way too large to manage. If you want to calculate something related to your population, you have to reach out to all the subjects in your population, which is really difficult in most cases. So what you have to do is you have to collect an appropriate sample and then project that results to your population. So it's really important that you select a good sample which represent your population. If a sample is not good enough, it's not representing your population, definitely your projections, your analysis is going to give you wrong answers. So for example, if you think about, you need to calculate the average age of a BVC student. So this number, let me change the color. I don't know why I had red. So this number is actually about the entire population. So if you want to calculate the average age of a BVC student, you need to contact each individual student currently enrolled in a program, get their ages, add them all, divide by the number, you get the average age. So basically this is what? This is the population mean, mu. So that is the number we want. But unfortunately, there are so many students, it would be extremely difficult for you to reach out to each individual student. So because of that, you have to compromise and go with a sample. So what you will be doing is you will be using one of those 4 methods you've studied. Simple random sampling, systematic random sampling, stratified random sampling, cluster sampling. So you have to use appropriate sampling technique and then gather a sample of BVC students. So the number, how many students, really depends on your technique that you use, how much resources that available to you, what's your budget, what's your time, how many people that you are going to have in your group which assist you with this data collection. So based on that, you have to decide the number. So let's assume that you could reach to 1000 college students and got their age. So you have 1000 ages in front of you on your Excel sheet. So if you calculate average of those 1000 ages, what you will be getting is sample mean x bar, right? So one of the most important things you should understand is that population mean is what you want, the exact value. This is what you want, what you really would like to have. But since you can't get that number, you are stuck with this. So this is what you have. Right? So what you want is not the same as what you have. So quite rarely you would ended up having the exact number. So mu, population mean, is not same as your sample mean. There's always a gap. So this is where the actual value, let's just assume that this is where it is, and let's say your actual, the number x bar is somewhere here. So this gap between the actual average age of a Bow Valley College student and the sample mean age of a Bow Valley College student, that gap is called sampling error. The error due to sampling. Okay, so any good statistician, any good researcher would try their best to minimize this gap. So what they would do is they would try to pick a sample which represents their population the best possible way, so that your mean is so close to the actual number. So very low amount of sampling error. So the more your sampling error is small, your further analysis, any predictions that you're going to make based on this result is going to be accurate. So for example, if the sample average age of a Bow Valley College student is really close to the population average age of a student, then that is the best a number to use for further analysis. If your sample is a really bad sample, meaning actual number is here, this is what you got, there's a huge gap between the actual and the reality. So then if you use this number into further analysis, your analysis will go really wrong, right? Because the actual average age is a lot lesser than what you calculated. So you are thinking that more matured students are enrolled in the courses. That's your conclusion based on your sample, but it is actually not, right? A lot more younger people, average typically there are a lot more younger people enrolled than matured people. So it's really important to minimize the sampling error. Sampling error is very important. Extremely important. Right. And then, so this kind of gives us the entry to our next part 2 of the lesson. So in part 2, we are going to talk about this theorem. This is one of the profound theorems in statistics, or perhaps in applied mathematics, called central limit theorem. So central limit theorem talks about, so if I go back to this scenario, so you know for your study you're just going to have one sample, right? You're not going to have multiple samples. You just have a sample of 1000 students. But this is not the only sample that you can get, right? So you have around 15,000 students in your population. So there are so many different ways that you can draw a sample of 1000 students. So sample for a given sample size can be more than one option. So you can, for a given sample size, you can draw many possible samples. So central limit theorem is going to study the behavior of the sample means of all those possible samples. So central limit theorem is basically going to talk about the distribution of the sample mean x bar as a variable between possible samples of a given size. So if you just imagine, so just list of samples of size 1000. You have that list, and then their sample means. So you're going to have different lists of samples of 1000. So you're going to have a list of ages, 1000 ages in each sample, right? So 24, 29, 31 up to 1001, let's say 30. So this is sample 1, S1. and then you can talk to another 1000 students out of the population. So you're going to have a different sample there, so different numbers. Again, you're going to have 1000 ages, and then S3 can be another different 1000 students from the population. So that way you can think of all possible samples of size 1000. 20, I don't know, say like that. So you can make a big list. So this list usually has so many different samples. And then for each sample, so for each sample of 1000, you can calculate its sample mean. So for this, I don't know the number. Let's just assume it's x bar 1. Let's just assume, okay? Again, I don't know the number. If I add all the 1000 ages, divide by 1000, let's say I got 24.5. And then do the same with second possible sample, x bar 2, say 25. And then doing the same thing here, x bar 3, 28, so and so. Okay, so now you can see between samples, sample mean acts as a variable. So x bar is a variable. Between samples, from one sample of 1000 to another sample of 1000. So x bar, even though up to this point we thought, okay, sample mean is a unique number, it's just one number, fixed number. Yeah, that is true, but it's fixed for one sample. But when you think about all possible samples, then it's not going to be fixed. It changes from one possible sample to another, right? Hence, it acts as a variable, because that's the idea of a variable. Changes from one subject to another. So here, sample mean changes from one sample to another, right? Okay. So when you have a data set like this, so now you can just assume this is just your data set. So if you just think of this as your data set, whichever numbers you get here, and you can plot it. You know, when you have a data set, numerical numbers, you can plot its histogram. So now on the x-axis, you have sample means. So 24.5, 25, 28, and there will be many more, right? So what happens is, when you plot this whole list into a histogram, it is going to look, this is why it's so interesting. This is why this central limit theorem is so interesting. When you plot all these possible samples of size 1000, you are going to see the bell shape. Okay, that means for a given sample size, the collection of sample means is going to be normally distributed. The distribution of the sample mean is normal. Okay, so now I'm going to write it down. Now I'm going to write down the central limit theorem. So this is what exactly what central limit theorem says. says regardless of the population for a large sample size, we usually say large means 30, sample size is 30. Regardless of the population for a large sample size, the distribution my handwriting is awful on this thing. The distribution of the sample mean x bar is approximately normal with mean equals to population mean, mu, and standard error. Standard error is exactly same idea as standard deviation. Standard error sigma over square root of n. So if you just refresh your memory on what we did in chapter 6. In chapter 6 we talked about the similar idea. You have a variable, and if it's normally distributed, you should know the mean and the standard deviation to talk about probabilities, right? So central limit theorem in a way allows us to talk about probabilities for sample mean as a variable. So it's not just the variable, it's the mean of the variable. So if you go back to your example, in your example, you have two things. One is your variable, population variable. So now we have to call it population variable, because now you have actually two variables, pop variable. So this is x, let's say it's x, and this is what? Age. Age is your population variable. And then the other variable is the mean. This is variable 1, this is variable 2, is x bar, average age, mean age. So what the central limit theorem tells us is, regardless of this, we don't know what distribution this has. If you manage to get all ages, for example, if you assume that you have 15,000 students at Bow Valley College and somehow you manage to get all their ages, and then you plot it. So some weird shape, I don't know, x-axis you have age, okay? So it obviously does not look like a normal distribution, right? But regardless of that, it doesn't really matter. If you pick a sample of 1,000 students, 1,000 ages, then if you think about average age, distribution of average age for n equals to 1,000. That is going to look like a bell-shaped curve. Okay, so regardless of the population, average age is going to look like a bell-shaped curve, symmetric around the population mean, mu, whichever number it is, and then the standard deviation, standard error, we call it standard error, because the population distribution has a mean and a standard deviation, right? Where is the center of this distribution? What is the spread of it around the mean? That's those two numbers. So similarly, now that x bar, average age, is also a variable, it also has a mean. It is the same mean as the population mean, mu, but it's not the same standard deviation. It's a bit lower than that. It's sigma over square root of the sample size. Okay, so if I summarize once more, we have two variables, variable x, variable x bar. So mean, standard deviation. Mean is still the same, standard deviation is not, and we call it standard error. Okay, right, so moving forward, especially during an exam, when you have to calculate a normal probability, now that you have two variables, you need to figure out which one am I dealing with. Is my variable just the age, or is my variable average of it? So the questions could go like this. So I'll give you an example. So for the variable x, age, say x is age. So age is normal. It says that age is normal with mean 24 and standard deviation of let's say 2. Okay, and then you randomly pick any student at Bow Valley College. What is the probability that their age is more than 25 years? So the question is, what's the probability age is more than 25? So this is exactly what we did in chapter 6, right? So we run a megastat with this information. So you have mean 24, standard deviation 2, and then you're reading 25, right? And then you get the upper reading. There you go, you have your answer. And in chapter 7 now, this is what you're going to get. Chapter 7, it's going to say average age, or let me redo that. So chapter 7, it's going to say, it's going to give you the mean age is 24 and standard deviation is 2. It's going to have those information, period, and then it's going to say for a sample of, let's say 30, let's say 50 students. So now it's going to assume, okay, we are going to draw samples of 50 students from the entire population. So think about all possible samples that you can draw of 50. Think about their sample means, and then for a sample of 50 students, what's the probability that their average age, here comes the difference, is more than 25. Okay, so pay attention. So probability, oh, that's not good. So probability, let me use the highlighter. Probability age is more than 25. And here, probability average age is more than 25. So in one case, just the variable. In the other case, mean of the variable. Okay, so now when you run megastat for this one, now that we know we are dealing with the average age, go up here. So for the variable x bar, mean is same as given, standard deviation is not, it's different, right? So you have to make that adjustment. So mean still the same number, you just read 24. Standard deviation is not 2 anymore, it's 2 divided by SQRT of the sample size. So compare the difference, guys. Compare the difference between the previous megastat run to this one, and you're reading 25. Still, you have to get the upper reading because it's more than 25. So just do this side by side comparison I did here. Okay, so this is chapter 6 question. This is chapter 7 question. Okay, so the major difference comes into standard deviation. Okay, right. So that's all the lesson. So this is what you're going to do next. This is what we're going to do in our practice. So we are going to go through practice questions on how to calculate the probability for the variable average instead of the population variable. So I'm going to address the practice in my next video. So before you move on to the practice video, I want you to watch this again and then just try to get the idea of central limit theorem first, and then just try to get the idea of the comparison, like what we did in chapter 6 and what we are doing now in chapter 7. And in a way I like recording these videos because in face-to-face classes, once I explain the concept, if you miss something, you are going to miss that, right? There's no way you can rewind and listen, but you have the ability to do that now, right? So if you miss something, if you didn't understand anything, you can rewind as many times as possible as you want and go through it until you understand it, right? So go through this video, and like I said, if you run into any questions, write that down, and then you can always ask me those questions during the office hours. Okay, right. So if you understand all the concepts in this video, I would suggest you go ahead and start working on the practice video.